Yeah, hi. My name is Martin Thiede, and this is my colleague Oliver Müller. We are with Accenture Industry X, but actually, we worked quite a long time for a company called ESR Labs, which has been acquired by Accenture, and we are in the automotive industry since 20 years now, and we are doing automotive embedded software with C++. And recently we started an open source project, which is OpenBSW. It's called OpenBSW, and we are happy to get the chance that today we can present it to you. So what is OpenBSW? It is what we call a base software for automotive microcontrollers. So it's embedded software operating system plus anything else you need. So in embedded software, you might know the OS is not everything like on Windows. So you have all the drivers and so on separate from the OS kernel itself. So this is a whole stack, or it's supposed to be a whole stack. And it's supporting automotive standards. It's supporting automotive safety and security, at least eventually. It's open and extensible. It follows on a code-first mindset, which is also a little special, as you will see in the next slide. It's open source and it's under the Apache license. So why do we need this now in the automotive industry? Of course, there are software stacks in the automotive industry which are being used. So why did we start this project? Why can't we just use, an existing software like Zephyr or other stacks which are already there? And the first thing is that the automotive industry is a little special. So first of all, depending on which ECU or control unit you look at, it's rather deeply embedded. And of course, it's resource limited, as you often have in embedded software. There are safety constraints, there are reliability constraints and requirements, of course. Often we have to run on a low power, we have to sleep, the ECU, we have to wake it up. We have all the vehicle buses, which are special. And this often means that we also have to do code generation, because if we need to fit all the code in a very compact format, then often there is no other way than having to resort to a bit of code generation at least. And the other thing is that right now the stacks in automotive, they are looking quite differently. So what we are doing with OpenBSW is really a really different thing, because the stacks which the industry uses today, at least for the microcontrollers, they use GUI-based configuration tools and a lot of code generation. So code generation is all over the place. You don't really, when you configure the stack and everything, you click boxes, and it's not like programming. And so that's why this really sets us apart from the existing way of working. So we are not GUI-based. The others have a model-first approach, code generation everywhere, and there is an automotive standard which the existing stacks follow, and this is also very strict. And in the end, it's hard to extend, and it's also hard to use it in continuous integration projects. And that's what we enable with this with our OpenBSW project. Then I will hand over to Oliver.
So we, as Martin said, we have been doing this quite for a long time already. So I guess around 20 years that we did the first C++ systems in the automotive industry, and it was initially not very well regarded, because everybody said it's like not a good idea to use C++. But anyway, I will show you a little bit about the what we are aiming for, or what might be some challenges. So I mean, I don't need to tell you as an audience what the advantages of C++ are, but I think it's really noticeable that since we switched our stack to C++, we gained a lot of useful concepts from C++ and could use them. And of course, it's since we are running in this kind of constrained environment where everything is like really needs to be deterministic, and we for example, we cannot run into any situation where there is no memory left on the system because we don't have memory anyway. So we are using C++, but we are restricting ourselves. For example, we are not using the regular exception handling. We are not using any dynamic memory allocation. So we work without a heap. And then we also can guarantee that we do not fragment our memory, for example. We unfortunately cannot use a lot of the nice libraries in C++, so basically we are not using any libraries at all. And that means we also implemented our own version of the standard library that fits to our needs. And I don't know, for those of you who don't know a lot about automotive embedded systems, it's usually not a system that runs on a Linux. At least the kind of controller that we're implementing systems for, mostly is a very, very basic system that is barely more than a scheduler. And or might also be that it is a bare metal system. But still, we have to face the same problems. We have to allow for concurrent access to shared resources. We have some real-time constraints that we have to follow. And so those systems, those operating systems, like for example FreeRTOS, they are running on a preemptive scheduler. So whenever you have a couple of tasks, and so what are the threads in those systems, and whenever there's a higher priority task that wants to run, the lower priority task will be preempted, and so you get this kind of scheduling. And interrupts are another nicety that you always have to deal with in those systems. Yes, and just to give you an example how that might look like, so we basically statically configure our operating systems with a couple of tasks. They are assigned priorities, and then so that when the lower priority tasks run, it is immediately interrupted once there is a higher priority task that wants to run, execute code, and so on. So the way that we build up our systems is, I mean, we make use of C++ to really compose our systems in a way that we can see the dependencies, and like as Martin said, we don't have any configuration tool that we use. We just implement our systems or implement the whole system as a composition of subsystems. Yeah, so we use dependency injection and keep a strong hierarchy so that the lower level systems, they don't of course know anything about the higher level systems, and you can introduce direct dependencies. So how does it look like? For example, then if we compose such a system, we are basically stacking those subsystems in run levels, which means we can also, on the one hand side, we can establish a layering for dependencies, where higher level systems can depend on lower level systems, and we also can enforce a strict way of starting up and shutting down a system in a very defined manner, so that we really can make sure what gets started up in what sequence. So this is how this might look in code then, where you can see that this is like our way of composing the system. We have a lifecycle manager that will that we can add those different subsystems to, assign them a level and maybe also some task context that is then used if those systems need to run specific code in their respective tasks. And then this is like part of our main routine, basically, to stack up those systems at runtime. And what you have might seen here is that we do always this emplace call on our systems, and that's how it looks like. So basically, as I told you, all the memory is statically allocated. So we only can do static objects, and what we do is we use this type mem, where we can, with it's a templated function that reserves just the right amount of memory for our type that we want to create the instance of, and so we can create those static objects. And that's all that it does. Once you then call this in place, it will use placement new and directly put your object into the space that you reserved in advance. So, yeah, I mean, also one important reason why we are doing this is in this way we can absolutely control the order of initialization. So we can control when our constructors are called, because if we just put them in our source files and create those global objects, static objects, then we can, it's very hard to control the order of initialization, and since they depend on each other, that's really important to us. Another aspect is that is a nice fallout, that we usually don't need to use constructors, and therefore we don't want the constructor code to end up in our binary. And with this approach, we can implement the constructor of this type mem empty, and what the compiler then sees is it will compile all the constructors, and eventually it will see the destructors are not called, and they are just optimized away then by the linker, and we get rid of a whole bunch of code that we would have had in our ROM anyway. So as we do not run on any reasonable operating system, we can unfortunately also not use something like standard thread. So we have to we make use of some abstraction concepts that we thought about, how we can then easily port our code to different operating systems. So we came up with this async lib that we have, and that allows us to actually put some piece of code and put it to assign it like a task context or a thread ID where it should run, and then it will be executed in this task context. So everything that we have there that will be then possible once we implement this for the respective operating system is we can just execute some code in a different task context, or we can schedule some code, or we can also schedule it repeatedly at a fixed rate. And that's also that allows us to be very, very portable, and it's very easy to port to a new system that we don't support so far. Martin, you wanna?
Yeah. So, for example, we are running on FreeRTOS today, and by this we for example ported it to Zephyr OS, which basically gives us best of both worlds. So our automotive specific parts based on are running on this Zephyr platform, which is really supporting a lot of embedded software targets. I think we're a bit over time already. Not sure how strict you are with the time. 5 minutes, okay. Okay, so one more slide, code-centric. I told you that the current stack use a lot of GUI-based programming and modeling. Oliver just said we don't use any configuration tools. I mean, it's not 100% true because, as I said, we have to do some code generation, but then we want to do textual languages. So we come up with our own DSLs to configure the respective code generators. For example, we have a language for describing the many messages which need to be sent on the bus, because in a vehicle you have lots of buses, you have lots of messages, they have fixed size, timings and whatnot, and this is configured by the car maker, and every ECU supplier has to, of course, adhere to this, and so you cannot just program it. You want to make sure that you 100% confirm to or you 100% stick with your car maker's what we call a message catalog, and then we import this, put it in our own textual language, and then we generate some code from it. And there are a couple of other cases where we do something like that. Okay, yeah, I think that's it. I mean, if you're interested, you find this project on GitHub, and otherwise, yeah, we are here in the break after the second lightning talk, so you can come to us and talk to us if you're interested. Thank you.
So anyone have questions for them? We may one or two.
What is the minimum of footprint in regard of flash and RAM?
Well, it really depends. I mean, there are small microcontroller ECUs which maybe just have 128 kilobyte of flash and 32 kilobyte of RAM, for example. That would be a rather small one. But then it goes up to a few megabytes of...
I'm not talking about the chip. Sorry, I'm not talking about the chip. What's your environment produces at a minimum code size and data size?
I'm not sure if I understand the
footprint in that. So the footprint in these controllers. How you say 128K flash is the minimum, and 60K RAM also.
Mm-hmm. You mean how much our stack uses of that?
Yes.
I mean, it really depends what you configure, because, for example, if you have a large number of messages, you need a large number of message buffers. So, I mean, we can fit into a 128 kilobyte flash, I would say, with some small application. But if you have a really large application, then, of course, you would not fit into that one, but you fit in a bigger one. It's fully configurable.
No, I mean, what is the footprint of Hello World?
The footprint of Hello World, a few kilobytes. I mean, not very big.
A few kilobytes.
Yeah. I mean, okay. I mean, if you have FreeRTOS and everything, then it will be larger. Okay, it's not 100%. I mean, in this case, it's probably more than a few kilobytes. But for example, on the Zephyr platform, which is very similar, you can even strip down the OS. You can turn off the OS features, and then it comes down to a few kilobytes.
Okay, we have one last. Please try to make it short.
Just a small question about allocation of static memory. As I understand, during this initialization, we allocate from complete memory some objects, and then if we running out of the memory, then during this initialization we get a message, or how it's managed?
No, the contrary. We don't want any runtime errors due to out of memory. So what we do is we statically allocate it in global memory. So it's like a global variable. It's in your linker script. You have it as a global variable. I mean, that's the most basic way. So basically we have stack data, of course, but the rest is like a global variable. And what we do, what Oliver wanted to say with the systems, is we build trees of C++ objects, and the root of the tree is a global variable. For example, we break it down a little more. So, for example, we have a communication system, and the root of the communication system is a global variable. It's an object which contains the other objects, like we have 10 buses, then we have 10 CAN driver objects, we have an Ethernet driver object, and they are childs in this, but in the end, they all form a global variable, and they are statically linked they are placed by the linker in the memory at a fixed location.
So this construction happens compile time?
Yes, at link time.
Okay.
So I mean, the only memory that we can run out of is the stack memory. Yeah, we can exceed our stack.
Yeah, I understand. Thank you.
Right. Looks like that's it. So thank you very much.
Thank you.